Okay, good afternoon, everybody. Thank you very much, first of all, to the organizers for having me and for the invitation. And before I start, I'd like in particular to thank my collaborators because part of what I'm going to discuss is partly based on work with them. This is Song-Ju Lee, Wolfgang Lehrtje, Guillermo Lockhart, who's also in the audience and who is an expert on modular forms and many of the topics that are being discussed at this workshop, and who will be able to answer any questions if I can. And in the last part, I will also be commenting or discussing a paper with Song-Ju Lee, Max Wiesner, and Daniel Klever, who is also in the audience. Okay, so in case we've forgotten, this is a workshop partly at least about the swampland. And the motivation of this work is indeed to connect to one of the conjectures which Irene discussed in her very nice overview on Monday. Namely, we'd like to test quantitatively the weak gravity conjecture, the sublattice weak gravity conjecture, and in particular for four-dimensional theories with minimal supersymmetry as an extra challenge. So we'd like to test the tower or sublattice weak gravity conjecture in ideally chiral 4D n=1 gauge theories or quantum gravities, in fact, gauge theories coupled to quantum gravity. And recall that this was the conjecture that in every gauge theory, for example, a U1 gauge theory coupled to quantum gravity, there should exist a tower or sublattice of states whose charge to mass ratio, so the ratio g(nu squared times q squared over nk squared, is bigger than or equal to the charge to mass ratio for an extremal black hole, which is a function of 1 over m Planck squared, m being in 4 dimensions, times some number, which in this case is 1, but may change depending on quantum corrections. So does there exist a tower of states with this property? And I'm stressing that I'm interested in 4D n=1 because this is closest to the world that we live in as far as we allow for a little bit of supersymmetry. And in such theories, there are no BPS particles. So we do not have the luxury of using BPS-ness in space-time in order to deduce the spectrum. So in particular, there are no BPS particles. So we need other methods to control the spectrum, control the massive spectrum of our quantum gravity theory, and then test this weak gravity conjecture. I will be doing this in the context of string theory, a string theory that yields a 4-dimensional n=1 theory. There would be various ways of compactifying string theory to 4 dimensions. And I'm going to use my favorite laboratory F theory because this is a very general one, but similar statements with different technologies should then hopefully hold also in our dual frames. So the particular setup that I'm going to use is so-called F theory, but this is just because I need a laboratory to test this explicitly. So I pick this one, 4D n=1 compactification of F theory. I will say much more about what this means. The key player for now, so more details will be filled in when we need them to those who are not string theorists, on an elliptic Calabi-Yau fourfold. What do we mean by this? For now, we need, for this motivation, we only need the following statement. We have a physical theory in higher dimensions. We compactify to 4 dimensions, and the information about this theory in 4 dimensions is encoded in an elliptic Calabi-Yau fourfold. So it's an elliptic fibration. This is a Calabi-Yau fourfold. It's elliptically fibered. There is a fiber E, which is a torus, generically. So the geometry would look like this. The cartoon, we have some B3.
So the F theory lives in 12 dimensions?
Yes. So in fact, you should think of this. Let me say this. In fact, in 10. I mean, this 12 dimensions that doesn't exist. That's the torus is just a bookkeeping device to keep track. It's really a 10-dimensional theory. I mean, type 2B theory with several. I'm coming to this. So the fourfold is given as an elliptic vibration over a complex threefold, which is a Kähler threefold. The elliptic fiber degenerates over the discriminant. There is a divisor delta. This is in H4 of the base. This is where the fiber degenerates somehow. And the claim is we take a 10-dimensional string theory called type 2B, compactify it on the Kähler threefold to 4 dimensions. And this theory includes also so-called 7 branes, which wrap the discriminant locus. That's the slogan. So we compactify. What we really do is compactify type 2B string theory. This is a 10-dimensional theory on B3. So we get type 2B on R13 times B3 together with 7 branes. 7 branes are objects that have 7 + 1 dimensions. The 7 branes have world volume R13 times S, where S is a component of the discriminant. Loosely speaking, it's not completely precise, but it's some device, it's some component of the discriminant. That's the same. Okay. And the different types of 7 branes give rise to a gauge algebra in 4 dimensions. We have states charged under this gauge algebra, and we want to know if there is such an infinite tower that satisfies this relation. Are there questions on this setup at this crude level from the mathematicians?
Yeah, so the discriminant is a curve?
It's a divisor. It's a 4 cycle on the base. So it's codimension 1 on the base. Other questions? Okay. So we have on from each 7 brane.
Sir, by branes, do you ask for some geometric property or just whatever submanifold of correct dimension?
So, well, a 7 brane in string theory, this is an object that has 7 + 1 dimensions, and that has certain physics properties. So it has a charge, and it has in particular a mass, a tension. So we think of this as stuff. For the mathematicians, this is stuff that fills 7 + 1 dimensions.
But is it in particular on the internal manifold? Is it a complex submanifold?
Absolutely, yes. So delta is really a divisor. You can also say that this is in pic. So it's a divisor. It's a complex 4 cycle. This was implicit, so we have really complex vibration. Nice complex vibration.
Be careful with the domain rule.
Ah, the domain rule. I like to cross the thing. So the pandemic was hard on us. I need to earn miles, and I usually do this by going. Sorry about this. Okay, good. So the 7 brane is associated with the gauge algebra. So for every type of 7 brane, we have a certain gauge algebra in space-time, so a certain gauge factor. And what we need to know, and this is the last thing we need to know for now, is that the gauge coupling of this gauge algebra scales like the volume, the Kähler volume. This S is in particular a Kähler 4 cycle, the Kähler volume with respect to the Kähler form of B3 of the cycle S.
Sorry, yeah, I have a question. So the 7 branes, these are not Dirichlet branes, these are like NS?
These are Dirichlet branes. Oh. You can think of them as Dirichlet branes or a more general object, so PQ7 branes. Bound states of Dirichlet branes and duals thereof under a certain SL2Z geometry. Think of them as D branes. Okay. I avoid the word because this is more general, but other questions on the nomenclature from the mathematicians? The physicists, of course, all know this. Sorry for boring you with this. Okay, I'll say much more when time comes, but for now I want to not lose the punchline. Okay, so another thing that Irene taught us on Monday is that it is the best idea to first study the weak gravity conjecture in the regime of weak coupling, so where G unknowns goes to 0. This is on the boundaries of moduli space. at infinite distance in the moduli space, a concept that will be discussed in much more detail in the second part of this workshop. So we will be following this advice and look at the weak gravity conjecture in the limit where G and Mills goes to 0 for those 7 brains. So the simplest regime is the one where we have a weak coupling regime. This is really just for computational purposes. If time permits, we will see what happens as we go away from that boundary. So we are for now interested in the asymptotic weak gravity conjecture, asymptotically in moduli space. Weak coupling means small g, small gauge coupling means the divisor S must become large. So this obviously translates into the regime in the Kähler moduli space of the base, where one divisor, at least the one grabbed by the 7 brain in question, becomes large.
So J is the Kähler form?
Yes, JP3 is the Kähler form on P3.
So asymptotic weak gravity conjecture is a synonym of distance from that.
Yes, in that limit. In that limit. So we are interested, so we need to study things in the infinite distance limit of in Kähler moduli space, where the volume, I omit the J, or maybe not, of our 4 cycle on the base goes to infinity. Okay, so such limits can be classified. This would be a talk by itself. I'm not going to say much more other than the result, because I'm still in the context of motivating the appearance of elliptic genera and so on. So the result of a classification of those Kähler limits, so the limits where at least one divisor of the base goes to infinite volume, those limits have been classified in a paper with, specifically in F-theory with Song-Julie and Wolfgang Lerche from 2019. And we showed that there are 2 regimes for this, namely a decompactification limit. This is one where the total base volume goes to infinity, states become light, and the lightest tower of states is a KK tower. This is mainly addressed to the physicists. Lightest tower of states is a KK tower. Proving the weak gravity conjecture for such limits is not what I'm going to do. This is a topic for a different talk. Instead, I'm going to look at the second possibility. This is case 2, the emergent string limit. This is the one where we can make contact with the topic of these lectures. Emergent string limit. Namely, this is the one where the following thing happens. B3 admits, in order for such a limit to exist, B3 must admit a P1 fibration. So the base itself must also be fibered over a P2, say, with a generic fiber P1 fiber, which may or may not degenerate. Sometimes we will be calling this curve C0. And the fibration, so this is a topological requirement for the limit to exist. And then the limit consists in taking the volume of the P1 fiber to 0 and the volume of B2, more precisely of a section of this vibration, to infinity in a certain way, which I'm not going to dwell on more because it would deflect from our actual interest. So that's the claim.
Sorry, why controlling this Young-Mills Calabi constant squared is enough to check this thing? Because you have
no, it's not enough. It's a I want to go to a framework where the theory becomes as simple as possible. When the gauge coupling is small, the theory becomes as simple as possible, as we will see. A nice dual description of the theory will emerge. with which we can tackle this problem.
Okay, so you still have to calculate the other quantity.
Absolutely, no, then the work begins. I'm just setting the stage. I'm still setting the stage.
So the fourth cycle whose volume you're sending to infinity, it's precisely the discriminant locus?
It's not precise. It is. You can think of it either as a component of the discriminant locus, or in fact, even that is a lie. I will say more what it is next time. But think of it morally as a component of the discriminant, not precisely, but some four cycle on B. So, but the statement is whenever any full cycle, I pick any full cycle S, whatever it is, and in order for this, the volume of this to go to infinity, two things can happen, either the first case or the second case, where essentially the fiber of this B3 becomes small while the base becomes large. And then the cycle S may sit somehow in this fibration. So we would have then the picture of B3 being itself a fibration over some base B2. And over all of this, we have our elliptic fibration that makes out Y4.
So B3 need not to be Calabi-Yau, right?
No, B3 is not Calabi-Yau. It is a Kähler threefold of positive effective anti-canonical bundle. In fact, in order for an elliptic fibration to exist, non-trivial elliptic fibration to exist.
Then I don't know what means compactifying that with this.
In the presence of 7 branes, when we have 7 branes, you have localized sources which will curve your space. And hence it's not Calabi-Yau. Okay, so this was all motivation. And now comes the point. Once we are in such a regime of where the base has this nice structure that there is a P1 fiber that becomes small. So the volume of this goes to 0, while the volume of the base goes to infinity in a certain way. Then the following, physicists are invited to look at the following object. Type 2D string theory has 7 branes, D7 branes, but it also has D3 branes, Dirichlet 3 branes, which have 3 + 1 dimensions. And one can now consider wrapping the D3 brane on the P1 and to get a string in 4 dimensions. That's the jargon. So that's the last part of this jargon. So consider now a D3 brane in type 2D string theory, an object with 3 + 1 dimensions. And the jargon is wrapped on the P1 fiber, i.e. on the curve C0. In other words, we say that the world volume of the D3 brane is of the type R11 times the curve C0, where the curve C0 is the curve in B3 and R11 is embedded into our physical space-time R13. Yeah, I can consider such objects in the theory.
Is it located at some point in the base, or it doesn't matter?
See, it doesn't matter. The curve has a moduli space. It doesn't matter. So you can take any representative of the fiber class that you like, and it can move.
And the vibration is smooth, or maybe it's smooth?
The vibration can be singular. It can, in particular, for instance, the P1 fiber may degenerate over loci on the base. It doesn't matter at all. I can consider such objects. And when I do that, I get in my 4-dimensional theory, I get an object that has 2 dimensions, 1 + 1 dimensions. So it looks like a string. So I get a string-like object in our physical space-time R12. And in fact, it turns out, this is a fact, if I take this very special P1 fiber, which again was motivated by us wanting to take this limit, G is going to 0 and so on and so forth. So if I take this very special situation, then this string is not just any string, but it's in fact a heterotic string. So this string is a heterotic string. This means it has a worldsheet theory, which has the same characteristic properties as that of a heterotic string in the usual heterotic string theory, which is a dual string theory, dual to type 2, type 2b. So it is described by a certain two-dimensional n equals 0,2 supersymmetric worldsheet theory. WS, I abbreviate worldsheet theory.
But do you think this string propagating in B3? B3 is not a Calabi-Yau, right?
That's right. B3 is not a Calabi-Yau, but the string can propagate over the base of B2. In fact, if you know, I don't want to say this now, but if you know about heterotic F-theory duality, this is dual to a heterotic string on an elliptic fibration over the same B2. So we just deleted this extra dimension P1, and this would be the dual heterotic. Okay. And the point is now, we want to study the worldsheet theory of this string. We want to check if the excitations of this string satisfy the weak gravity conjecture. And in order to do that, we will compute an index for its excitations. This index is the elliptic genus that we learned about in a certain way. And it can be translated into geometric invariants on the Calabi-Yau fourfold by itself, the Gromov-Witten invariants. Let me write this down. So our claim is, and this we will see, I'm still in the motivating phase. The claim is,
what did WS stand for?
Worldsheet theory. Sorry, I was just being it. How much time do we have? Okay. The claim is, if the 7 brane S gives rise to a gauge theory with gauge group G, and for simplicity I take U1, but that doesn't matter. That's just for simplicity. And if the 7 brane has furthermore the property that the divisor S on which the 7 brane was wrapped, so somewhere here we have the divisor S on which we have a 7 brane, that S dot C0 is not 0. So for example, S could be wrapping the base, then it would intersect it once. Then the excitations of the heterotic string that appears, emerges, becomes tensionless of the heterotic string that we just looked at from the 3 brane on R11 and C0 satisfy the Tower weak gravity conjecture. And in fact, the sublet is weak gravity conjecture if the theory is chiral. So if the 4D gauge theory is chiral. And I will say generically, we will see what this means.
When you say that the 7 brane gives rise to a gauge theory, you mean like the worldsheet
theory? The world volume theory. So the 7 brane fills 4 dimensions, and on this world volume filled by the 7 branes, we have gauge fields propagated. Thank you for this question. Yeah. Right? Okay, it satisfies this sublattice weak gravity conjecture in the limit. Here goes squared. Goes to 0.
Why do you need chirality for this?
This is only because I will need to argue that I have a flux background. The flux background will be important for us in order to argue that the elliptic genus is non-zero. But fortunately, flux background is also needed for chirality. And therefore, so this is just a technicality. Most likely this holds also in the non-chiral theory, but there we can show it.
And this appears in 4n = 1 percent. The 60 analysis, it doesn't matter.
And in the 6D analysis, this works just as well, yeah. And there the theory is chiral, is always chiral because it has 0-4 supersymmetry, the space-time theory. 1,0, the space-time.
Is it possible to rephrase this condition of the 7 brane in terms of the heterotic theory?
So the gauge degrees of freedom on the 7 brane are dual. If this relation holds, the gauge degrees of freedom on the 7 brane are dual to the gauge degrees of freedom that come from the heterotic.
Yeah, and the fact that this first condition of the 7 brane gives rise to a gauge theory with G equals to U1. Can one describe this in terms of the vector bundle on the?
Absolutely, yes. So this means that in the dual heterotic string, we have a vector bundle of type E7 times E8 embedded into E8, which breaks it down to U.
Okay.
But it is true for any G, but I'm going to do the simplest one of being U1, but the specific form of U1 is not necessary. So this is just for simplicity, and chiral and generically is also just for simplicity.
Can you remind me very quickly what's the SL sublattice?
Sublattice weak gravity conjunction. There is a sublattice of all states of the full lattice of charges which satisfies the weak gravity conjunction.
So it's a weaker.
It's a weaker version, yes. Okay, so this is the goal, and we will discuss all this in detail and show this, but I want to tell you where we are going. So with this motivation in mind, we will now go to the more technical aspects. Namely, the strategy to show this is we want to compute an index-like expression for the excitations of this heterotic string to check existence of those things. So we want to compute index-like expression. And this is the elliptic genus, the Witten index, that counts a subset of the string excitations of the heterotic string. So we have two restrictions. First, we will not count all the states, we will only count an index for the states and only a subset of states. But this will be enough. If those extra conditions are satisfied, this will already be enough to kill the problem. Otherwise, you have to work harder. I will define this index from our point of view. And then we will use a chain of dualities to relate this index to geometry, namely to Gromov-Witten invariants, BPS invariants on fourfolds. So chain of dualities will allow us to map this elliptic genus to the Gromov-Witten invariants, a generating function for the Gromov-Witten invariants on the Calabi-Yau Y4 that we're working on, in presence of some background flux.
Timo,
Yes?
before you go, if I don't take a U1 group, is it any group or it must be embedded into E8 Gaussian? Can I take SU 1 billion or something?
Then you will not be able to satisfy this relation. S.C0 equals 0. Yes, indeed.
Can you say very briefly what chiral means here?
We will discuss all of this. So this means that you have that the number of fields in representation, say plus R, in the representation R, and the number of fields in the conjugate representation R, that they have not the same number. Number of states in representation R minus number of states in representation complex conjugate of R is non-zero. Like in the standard model, only left-handed or only right-handed field, for example.
No, and the index of the sublattice was given by the intersection number.
Exactly. This will give us the index of the sublattice.
This is still general, no?
Yes, yes, indeed.
And what is the, maybe you will talk about it, but what was the largest number? Or
The largest number is not
Can you
known.
repeat the question because I don't think.
The question is, so this we are really ahead of our time. So this will give the index of the subletters. The question was, what is the maximal value that one found? We didn't find very high values, maybe 4, I think. It's not known what the upper bound is.
So is asking ahead, what's the property, physical property of this subset with respect to the full spectrum, or nobody knows? I mean,
I'll discuss it in detail.
okay.
Everything here will be discussed,
Okay.
but I want to give you the upshot in case you need to take a train afterwards. So a chain of dualities map this to Gromov-Witten invariants. So we will compute them explicitly. Explicit computation is possible via mirror symmetry on fourfolds. But this is not even necessary because the generating function for the Gromov-Witten invariants or the elliptic genus have distinguished modular properties which already are enough to argue for the existence of the states that satisfy the conjecture. Distinguished modular properties of the elliptic genus will be sufficient to argue for the states of the subletters weak gravity conjecture.
I guess finding a contact sample of this weak gravity conjecture is completely out of reach, or is
Finding a counterexample.
yeah, meaning that ruling out some backgrounds via this concept, right? Checking that for all states, this is not going to happen.
In this class, it certainly works. Finding counterexamples, of course, is always more.
What I mean is that not counterexamples in the mathematical. What I mean is that ruling out some background.
No. This works for all backgrounds. Once I fix my class of F theory, this works completely general. I'm not. That's why I'm not really specifying. So in other words, this holds very generally in the background of F theory that I'm in.
I think our intuition is by construction it should work, because everything is consistent, is something compatible with quantum gravity. And if you find that this weak gravity conjecture is not satisfied, then you will be proving that the conjecture is wrong.
Or that background is not compatible with quantum gravity.
Well, it's a string theory construction. If there's nothing wrong with it, if it's not sick, or you're not doing anything wrong, it is compatible with quantum gravity.
Okay.
So either you're disproving the conjecture or you did something wrong.
Okay, I thought there was possibly a tool to rule out some background like this.
Maybe,
Yes.
but if the conjecture is not wrong, then it means that there is something wrong with the background.
How way to know string theory and the background? If you are convinced that you have all the ingredients, then maybe if it's a more complicated thing of Calabi-Yau or a thing that we don't know everything yet, maybe you can try to show that we are missing something.
But as Irene pointed out already, for example, one can quantitatively ask. So the question would be, if the subletters that satisfy this becomes arbitrarily large or coarse, then the statement would have no meaning. If only every state, which is a multiple of 10 to the 500, has to satisfy the conjecture, it's hopeless. So that's why we need to understand quantitatively how coarse the subletters can be. And this has translated into a geometric statement. I mean, this intersection number will give the coarseness of that letter, the minimal core or the maximal coarseness of that letter. And that's something that can be studied. And the result of this will be things always work as long as this doesn't get too large. And this is an unknown question in algebraic geometry. What is the maximal value that you can get here? It's related to the properties of the height pairing of rational sections.
Sorry, Timo, so I don't understand why that statement. So what does it mean? It means that in the end we don't need to explicitly compute the law?
Exactly. One can compute it explicitly in every example, but the modular properties are so strong that even without computing explicitly, I can show that the states are there. And in order for this, another spoiler, in order for this statement to hold, one actually needs very specific modular properties that are only present on Calabi-Yau fourfolds with fluxes, and which Georg is going to elaborate on in great detail in the lecture. Okay, so now that was the kind of the general directions. And now let's start. So the first would be the appearance of the elliptic genus in the present context. And I'm here going to use a formulation which makes contact with what was discussed at the very end of the last lecture. So this fits nicely namely with the Witten index. And this goes back, in fact, originally to papers by Schradekens and Warner, and then a paper also Schradekens, Warner, and Lehrte, and then papers by Witten at this time. So let's be general and let's consider a string, i.e. a two-dimensional n equals, and I'm now doing 0,2 supersymmetric. So for the left movers, I have no supersymmetry. For the right movers, I have two supersymmetries. Worldsheet with such supersymmetry, a string, a 1 plus 1 dimensional object, and I'm going to put it on a torus. I put it on a torus, so I'm having a torus in our space-time, and I'm assuming that our string grabs this torus. So one dimension of the string is of the one cycle, and the other dimension, except suppose we are in Euclidean space, would be on this other dimension. And the torus T2 have modular parameter tau. Then in string theory, one can compute the partition function of all excitations, perturbative excitations of that string. And the elliptic genus, as formulated by Schradekens and Warner, is a subsector of this partition function with periodic boundary conditions for left and right movers. That answers your question. With an index. So it's an object that depends on two parameters, q and psi. As follows. So I take the trace in the subsector of theory of states with periodic boundary conditions for the left movers and the right movers, RR for Ramond, periodic left and right moving. So only one of the four possible boundary conditions, periodic, antiperiodic for left and right on the torus. And one takes out the index, the Witten index, -1 to the f the fermion number for the right movers. In fact, one has to remove certain zero modes to get a non-zero result. And the partition function means I compute q to the h left, q bar to the h right, and I weight all this with the charges under a u1, which I assume I have. So here, q is e to the 2 pi I tau. That's why I got nervous when the 2 was in the and the psi is e to the 2 pi I z. Tau is in the upper half plane. Z is just a complex number. The q is the charge generator of a U1 symmetry which I have. So I'm assuming that on my string worldsheet I have a U1 symmetry that distinguishes the different states and therefore also to gauge U1 theory in space-time. So I sum over all the states with periodic boundary conditions left and right, but I have a certain index here, Fr being the fermion number. I weigh all those states, and to each state, I weigh the Hamiltonian for the left and right movers and also the charge. So this is the partition function. If I didn't write Ramond and that didn't put in this -1 to the Fr, this would just be the usual one loop partition function that you all know. And like this, it is a subsector, and there is an index, like counting problem because of the -1. That's
Sorry, can you recall what is the notation FR, HL,
so Fr, thank you, is the right moving fermion number. So if I have a fermion for in the right moving sector of the theory, I put a -1. R is the fermion number for the right moving sector.
So can we describe this subsector that comes from the Ramon sector in space-time as opposed to the rest?
It should correspond to, these are the states that lead to the anomaly in particular. So at the masses level, these states are the ones that give rise to the anomaly. And at higher levels, so one could complete them by level matching into higher states where they will also correspond to some subsector, but I don't have a good interpretation.
What this lattice means. I mean, I would just to give the lattice some intuition.
I can't really say what exactly they are. Yeah.
So massive casting.
Massive states and the subsector of the mass.
So I'm still missing what is HL, HR.
Oh, HL. Okay. HL is the Hamiltonian of the theory for the left movers and HR for the right movers correspondingly. So the idea is that I can look at the excitation levels of the string. You know, a string has an excitation level, and HR gives up to a shift of the vacuum energy the excitation level. So,
and here you have a EA cross field bundle, which is trivial over repeated.
So I can think of this as the hadronic string, but I can make this definition for anything. For any string, as long as it has at least a U1 on the world sheet, at least a U1 current on the world sheet. And I'm singling out this U1 current.
So you don't care about the gauge bundle in this.
I'm looking at the field at the conformal field theory on the string. I'm not looking at space-time. So there is a gauge bundle. Think of it as there being a U1 gauge bundle. You pull back that U1 field to the world sheet, and that will be that U1.
So you are treating this thing macroscopic. I mean, it's not the original microscopic string of string theory, but it's a macroscopic object.
Yes, it is. Exactly. It is a. I could treat it as the microscopic object, but this definition is much more general. It has any string which is just a two-dimensional field theory, and for which I can count the states according to this procedure.
So I don't have to think of this propagating anywhere. It's like
yes,
its own.
Exactly. You can think of this as just an abstract conformal field theory, if you like. Alternatively, you can think of this as the hadronic string on some propagating on some vector. The statement that is so true.
And the background is a torus in this case.
No, that's the world sheet of the string.
This is the world sheet of the string.
Yeah. I take it the partition function of the string. Okay. So as it turns out, due to the supersymmetry for the right movers, the trace over right moving bosons and fermions cancels out because I have a -1 to the FR. All the bosons and fermions in the right moving sector come at the same multiplicity but with opposite sign. Therefore, there is no dependence on Q bar left. So this is then just a power series, formal powers or a power series in Q and psi. So I have right moving supersymmetry. So I have 0,2 supersymmetry. So I have complete cancellation in the right moving sector. And therefore I get something, if I now hand it, that depends only on Q and not Q bar and on psi as a formal variable. So I can write this as a sum, Q to the N, psi to the R, with a multiplicative factor N of little n R for N bigger than or equal to 0 and R in Z, modulo a prefactor Q E0, where E0 gives the ground state energy. So the idea is we think of a string spectrum with excitations. These are here, this is here the excitation number, H if you like, n equal 1, n equal 0, n equal 1, n equal 2, and so on and so forth. We count all the states at the different excitation level. They come with certain charges. We also count them. R will, at each level n, only a certain number of charges will appear with different signs, maybe. And at level n equals 0, we will have some ground state energy E0. This would be the energy E0, the ground state energy. And since we are counting q to the h and not q to the n, we have to take this one also into account. In fact, this will be negative in the left moving sector.
No, sorry.
Yes.
So the presence of that FR in the trace,
Yes.
doesn't it kill all the right moving?
No, on the
parts?
other hand, it's supposed to take out certain zero modes. So
It's not, okay.
equivalent, you can remove it and say certain zero modes excluded
It's
so
not,
that you
it's
don't
not
get a zero.
equivalent as putting like the full FR.
No, no.
Okay, so
Sorry, I'm still thinking about Fernando's question. So HL and HR are eigenvalues for the zero mode of the Hamiltonian in the corresponding Ramon.
Yes,
Okay.
exactly. So for the HR, it doesn't matter because it cancels out. And for the HL, the eigenvalues are integers. So we get depending on the string excitations. And this is here for the L, modulo an offset at n equals 0. N equals 0 will have some energy, and then all the others will have this energy plus 1 plus 2 plus.
HL and HR are the same numbers, which are eigenvalues for the.
So you can view this as an operator acting on the states of your Hilbert space.
Oh,
Sorry, I should have said this.
okay, this is a series. Okay, now I
It's a trace over the Hilbert. I should have maybe have written over a Hilbert space for the string in the sector with periodic boundary conditions. Then you can view this as an operator acting on this, or equivalently as then the corresponding eigenvalues above which we. Good. Oh, not good. So the naive expectation would be this is a general statement, and now I'm going to apply this specifically to the types of strings that we have by wrapping a D3 brane on a curve on our Calabi-Yau as discussed. So naive expectation would be that Z of Q and psi, that this object here should be a meromorphic. There can be poles, for example, if E0 is negative, and the poles in Q, Jacobi form of a certain weight minus d over d minus 2 over 2, where d is the number of space-time dimensions, in our case 4, and of a certain index, elliptic index, m, some value in z positive, non-zero. That would be the naive expectation. Naive expectation based on intuition from purely perturbative string theory, or more precisely based on the results of Seligman and Warner, who proved the statement specifically for the heterotic string on toroidal orbifolds, where one has a perfectly perturbative heterotic string. And meromorphic Jacobi form means good transformation properties under the modular group of the torus. The intuition would be that we have here a partition function on a torus, which is artificially taken to be the world sheet. So therefore, under a modular transformation of the torus, the partition function should not change. So naively, we would think that it's completely invariant under a modular transformation of the torus. However, due to a certain technicality that Seligman want to describe, is having to do with zero modes, which have to be regulated and so on and so forth, one expects not complete invariance, but covariance with respect to the modular group. And this is something that is encoded in this modular weight. Let me write a statement. You would expect that, i.e. you would expect naively that Z of Q psi is the following object. It is a certain Jacobi form of weight W and M, which is an object from the upper half plane, cross C to C, upper half plane here we have the tau, our model parameter. In C, we have our Z, which is just to keep track of the U1 charge, such that, in particular, the following holds.
What's M? Like W is a weight, and what is M?
The elliptic, so-called elliptic index, it's defined by the following equation. Namely, if I take phi Wm and make a modular transformation A tau plus B over C tau plus B, and I transform also Z, as Z goes to Z over C tau plus D, this is a modular transformation, then we will have a covariant transformation C tau plus D to the power of W, and another prefactor e to the 2 pi I m times C over C tau plus D Z squared by omega m or Z. Plus one more condition that I'm not going to write down now. So this is the definition of a Jacobi form. This is the definition of a Jacobi form. It's a map of this type, which transforms under a transformation of this form in this fashion, plus one more condition that I'm not going to write. And the W is the weight, and the M is the elliptic index, and this describes this prefix. So Schenikens and Warner showed that if I take the heterotic string on a heterotic orbifold, nicely perturbative, in d dimensions, in our case d equals 4, then this is the transformation property of this elliptic genus defined in that form.
But the general story is supposed to be valid for any background.
Exactly, exactly. I'm coming to this.
Just quick question. So the information of the background is in these ends or E naught, or what is it gonna be?
The information about the background will be in this end, in these ends,
Which are
and in E naught.
So it depends on the model.
Absolutely,
Okay.
yes. So the N and R, this is the index-like number of excitations with at excitation level N, and with, in this case, U1 charge R. I had actually forgotten.
Is this a discrete quantity or?
This will be a number, exactly.
So if I have a moduli space, where does the moduli space information appear?
So this is a rigid object. This will not change with your continuous moduli. That's the whole point. But because it's an index, it's like, think of it as the chiral index and the generalization of chiral index also to all the massive states. It will not depend on your moduli. The specific type of background will tell you that there will be different values of n. Everything that will change, for example, your chiral index at the masses level will also change those numbers at higher level.
So it's like a wall crossing situation in which.
Yeah.
So only E naught depends continuously on the moduli?
Oh, you know, it also does not depend. Nothing in here depends continuously.
It's in a spectrum, so naively you
So that's the whole point. It's an index-like spectrum. Indices do not depend on the
So
model.
because you have done the trace there, no?
Yeah.
So that
But
otherwise.
the minus 1 to the f.
So otherwise you would have.
The minus 1 to the f.
Okay.
Yeah.
Sorry.
So this is not visible. This is not sensitive to vector pairs, which would come down up and down. Absolutely.
It's a partial information.
Yes, it's partial information. Yeah.
I also have one other question. So this is in principle the one loop partition function, right?
Exactly, but modulo.
Okay, yeah. So then in principle you have to make sure that in your setting that this thing is weakly coupled.
That's why I went to G angles to 0.
Okay.
This guarantees that also the string in question is a weakly coupled string.
Okay. So is the size of the P1 shrinking? That
Exactly. Then you have a weakly coupled string. It's vanishing tension.
One loop, you mean in alpha prime?
In the string coupling, the effective string coupling for the CFT goes to 0 in that limit that I'm looking at where G angles goes to 0.
Not a full line.
So sorry,
Yes.
before you right. So this you're taking the trace over the sublattice that is going to be your sublattice with gravity conjecture, blah, blah. And even if you're taking the trace, you're going to be able to tell me something about the sublattice, about each member of the sublattice, right? Because you want to check the gravity conjecture for all of them.
So I'm taking the trace over all the states that come from the periodic boundary.
Yeah.
Within those, there is a sublattice that satisfies weak gravity conjecture.
So it's a sublattice of a sublattice.
Yes, only very few of those states will satisfy the weak gravity conjecture. Which,
But you will be able to check it even if now this is not a property of any of these objects. It's just a trace. Well, okay, I'll wait.
okay.
Sorry, in the thing you're erasing, we were happily living on a two torus, and now you said that this is valid for any background. So
So the torus is a string on a loop.
okay.
Yes, I'm putting this string on a loop. Exactly. The one loop addition function.
Anywhere, flat space, non-flat
And this
space, Calabi-Yau, anything.
This is a string in 4 dimensions, right? I have compactified to 4 dimensions. In the 4 dimensions, I have an effective string, which came from something. And for this string, now I take my string on a torus and compute this trace-like partition function. But that's just a trick. That's just a bookkeeping device in order to keep track of those numbers here.
So there is no dependence on the background at all, not even in the topology.
So the topology of your background, which gave rise to your string, manifests in values in integral or half integral values of E0, up to half integral values of E0 and integral values of this. Once I fixed my Calabi-Yau and say I take the string from this particular curve, these numbers will be fixed. But then moving the curve in my Y4 will not change the number.
So how do you see from the picture you wrote there, or the T2, how do you see the background at all? I don't.
The T2, my background, so I'm in R14, R13 times T. This is my background.
Yep.
Now, in here I have a string, R11. Now I say, suppose you take this string and put it on a torus, hypothetically, and compute the trace, then this is what you will get.
Well, yeah.
So,
what I don't understand is the sentence and put it on a torus.
So
That
I think that the statement is you have a string propagating in the background. The string has some excitations, and this is sensitive to the background. So different background gives different excitations.
Yeah.
And then from here he computes something, which is the set.
Yeah.
And physically it has to do with one loop propagation of a string. So it's just like all these particles running a loop with this particular.
So you should think of the torus as a Feynman diagram here. Really the one loop of the string.
okay, no, I think
Okay, so this was the naive expectation built on perturbative string theory. It turns out the strings that we are looking at are more complicated, and there will be deviations from this. We'll find deviations from this naive expectation, i.e. an anomalous transformation behavior, and this will lead to this theory of quasi-Jacobi forms rather than Jacobi form that Georg will be discussing next time.
Is this the holomorphic anomaly?
Yes, holomorphic anomaly. There's a holomorphic anomaly. This gives rise to a modular and an elliptic anomaly. So the case is, since we are on fourfolds, is much severer than what would be happening on Calabi-Yau. So how much more time will I get? Tell me.
How nicely are you asking?
No. No. Or what's the time frame?
Typically like 5 more minutes, but we can.
Okay, because we had many questions. Yeah.
We can stretch it a little.
Okay. Okay. Maybe if you give me 10 more minutes, then I can do what I need to do. Okay. Good. So the claim is now, given this object is indirectly defined via my Calabi-Yau fourfold, right? Because I have a string wrapping a curve inside the base of the Calabi-Yau fourfold. And the claim is that these numbers here can be recovered in that Calabi-Yau fourfold as certain Gromov-Witten invariants. So that's now the relation to the relative Gromov-Witten invariance.
Okay, one question. So all of this computation was in genus 1, right? And,
Yes.
so you only get like genus 1 Gromov-Witten invariants, or like?
In fact, this is unrelated. I will get the genus 0 Gromov-Witten invariant,
Okay.
but it's unrelated to the torus topology. We'll see. Okay. So recall, here was our Y4. There's an elliptic vibration. over the space B3 with a projection pi. And now I need, unfortunately, another piece of physics information. Namely, namely, there are three theories that I can define on this Y4, which are related. Three related theories associated with Y4. Namely, the first is, I can consider so-called M theory. M theory is an 11-dimensional theory. This is an 11-dimensional theory. I can compactify it on Y4 to 3 dimensions. And I take the 3 dimensions to be R11 times the circle S1b. I can compactify alternatively a 10-dimensional string theory type to A theory on Y4 to 2 dimensions, 10 dimensions on Y4 to 2 dimensions. And this theory is the result of taking the M theory on this background in the limit where S1b, the volume of S1b goes to 0. So this is if S1b goes to 0. And the third theory, this is the one that we've been looking at all the time, that's F theory on Y4, or type 2b on B3 with 7 branes. That's the theory that we've been talking about. This is F theory on Y4. More precisely on Y4, essentially 12-dimensional, as I said, or I think 10-dimensional just on the base, times R11, S1b, S1a. Where I put another circle compactification S1a, the volume of this to 0, or the radius of this to 0. These 4 theories are related. This is standard in the in the F theory, M theory literature. And the point is now the following: take a string from a curve C on the base by wrapping it in 3 brane on this curve. So consider now a string. Consider F theory on Y4 and consider a D3 brane on R 11 times the curve C. C was the curve in B3, right? This was the picture here. Elliptic vibration on the base B3. We have some curve C on which I wrap a D3 brane. I get a string in 4 dimensions. Now, in fact, let me take, instead of R11, let me identify this with R times the circle S1a. So I have a string in 4 dimensions, which I wrap on another circle S1a. This gives me a particle in 3 dimensions, in the 3-dimensional M theory on R11 times S1b. This gives a particle in theory on R11 times S1b in M theory on R11 times S1b times Y4. And in fact, a BPS particle. Okay, taking the string, wrapping it on a circle gives me something that looks like a particle in the theory that I get by compactifying the 3-dimensional effective theory on the 4-dimensional effective field theory on the set. BPS particles in 3 dimensions in M theory from 3 dimensions are counted by BPS indices, which are in suitable situations the same as Gromov-Witten invariants. And this is the relation how the bridge that makes the connection between counting particles in M theory, between this and counting excitations of the string. So the statement is that these particles are obtained alternatively by wrapping in M theory. M theory is a theory in 11 dimension. It has a M2 brane, a 2 plus 1 dimension brane, and an M2 brane in M theory on a suitable curve on Y4. Counting these curves means counting BPS states, and the numbers that I get are the same numbers that appear in this elliptic genus. And I'll write down the claim of the dictionary, if I may.
And it's not the same curve.
And it is related to this curve. It's not exactly the same curve. But it is related to this curve. So more precisely now, let me specify to a particular setup. Namely, I have an elliptic vibration. I have here B3. I have here a curve C, which is usually called C beta in the literature, on the base. So this is the one on which I wrap my D3 brane to get the string. Now, I specialize now to the situation where I have one U1 gauge algebra, only U1 gauge group. In this situation, I know that the elliptic fiber of my fourfold will degenerate somewhere, doesn't matter where, in such a way it becomes singular. There's a nodal singularity I can blow up and then get a curve class in here. A new curve class in the fiber. That's of this type, CZ, the curve class CZ. And I have here an elliptic curve E. And the claim is, in my elliptic genus that I originally had, if I write this as Q psi as the sum Q E0 n r psi to the Q to the n psi to the r. If this is my elliptic genus, then n of nr is the Gromov-Witten invariant GW of a curve C beta nr, where C beta nr, a curve, is given by C beta plus n times the torus plus r times this curve CZ.
Can you explain the picture again? So,
yes. So I start with an F-theory compactifications to 4 dimensions with the elliptic vibration over the base. On that base, I had a curve class C. Previously, this was this P1 fiber, but any. We had said that if we wrap a D3 brane on that curve C, we get a string in 4 dimensions. For that string, we had computed this elliptic genus, and without saying what exactly it is, there will be some excitation numbers associated to this elliptic genus according to this trace count. And the claim is that these numbers which appear here have an interpretation as the Gromov-Witten invariants of certain curves. The curves are as given. I take the curve on the base on which I wrap my string in the first place, C beta. And then to get the number at excitation level n and with charge r, I add to this curve class n times the class of the fiber of the fourfold plus r times a curve CZ. This is a curve in the fiber, which is in one-to-one correspondence with the appearance of a U1 gauge symmetry, in a way that I will describe more next time.
what does the picture mean? This can be.
This is okay. Sorry. This means the elliptic fiber degenerates over a locus into an I2 fiber. So there's a nodal curve, and I resolve this nodal singularity, and then I get a Kodaira fiber of I2. Kodaira I2.
So if you don't have this curve, then you just have a quasi-modular form.
Exactly. If I don't have this curve here, then I would just have a quasi-modular form. However, for fourfolds, then the index would vanish. On threefolds, I could do that. And on fourfolds, Calabi-Yau fourfolds specifically, the index then would vanish.
But you can have elliptic Calabi-Yau fourfolds where you like elliptic Calabi-Yau fourfold over P3 or something.
Yes.
Where the Gromov-Witten invariants are non-zero.
That depends. Okay. This depends on the flux that you use.
Oh.
Another technicality, this I'm going to discuss next time. You have, in order now to specify these number of Gromov-Witten invariants on the fourfold, you have to specify a flux background. There are three types of flux backgrounds depending on their relation to this elliptic vibration. And only one of them actually corresponds to flux that gives rise to chirality from the F theory point of view. With respect to this flux, the elliptic genus is 0. But with respect to the other two fluxes, the elliptic genus then would be a quasi-Jacobi form or a quasi-modular form of weight 0 or -2. But to get the one of -1, I will need this extra refinement because this is odd under xi to -2. It's just a special, yeah.
Ah, so you expect odd weight and then
Odd weight, exactly, odd weight. Yes. But I will say this. But let me just say the statement. Gromov-Witten invariants now are defined with respect to a background flux. G. This is a class in H22 of the fourfold. This is the flux that I need to switch on in order to get a chiral index. And this flux will enter the computation of the Gromov-Witten invariants. And we will discuss this in more detail next time. Question? Sorry.
So, I want to get an intuition why there is this sum of n e. So is this related to the fact that you have wrapped on SA your
exactly,
and this was part of the elliptic fiber of Y4?
Yes.
So
yes.
Then the E would be the affine part of the fiber, and then the other one is the.
So you can think of it like this. So the N here is the excitation level, just to start with. But if I wrap on an S1, the excitation level for a wrapped string can be identified with the KK number corresponding to that circle.
But from the point of view of the blow up of the fiber, is the E is the affine part, and the CZ is the Cartan.
Yes, you can think like this. Yeah, so the N is associated with KK number from the wrapping, and the R is associated with the U1 charge, with the gauge charge, and this is associated with that.
And this was a consequence of the fact that in this whole duality that we discussed, the string is wrapped on
exactly.
What was part of the elliptic fiber before.
You can think of it like that. Yeah.
Okay. The background flux. What does this correspond to in the heterotic side?
It corresponds to part of it maps to geometry on the heterotic side. Part of it maps to gauge bundle on the heterotic side.
To geometry meaning.
Sorry, I take this back. It maps to the gauge bundle on the heterotic side. Okay. It maps to the gauge bundle on the
geometry meaning NS5 brane possibilities, or
no, the specific elliptic vibration. So we have a duality between F theory and heterotic.
So this maps to the bundle. So this corresponds to
this corresponds to the bundle data on the heterotic.
And in the calculation of the definition of this elliptic genus in the heterotic side. So you said that this is a calculation for one loop. Is it possible to recover this one loop calculation from a 0 loop calculation from 3 level or not?
So no. It is
no, because I think there is a mathematical definition of what the 3 level is, but I don't think there is a mathematical definition of what the one loop is.
Why not? No, conformal field theories have a, yeah, they have a tree level and a one loop, and from there you get everything by gluing. So
Yeah, I know. Yeah, but what I mean is that I don't think there is a good mathematical definition of what this elliptic genus means with bundle and so on at one loop. I think at tree level, there is one using this parallelogram twisted by a bundle.
I see. But I think this is now the language of the heterotic string. And there, I think probably the zero loop is what this will correspond to. Okay. I think the loop counting is not one-to-one in this nomenclature. When you say elliptic genus at one loop, this I think will not does not reflect the fact that here we did a string perturbation calculation at one loop. I think the loops are different loops.
So that's not the loop of heterotic of the heterotic string.
No,
it's the loop of the macroscopic string that you get in type 2D.
Yes. I think this object should map to the thing that you know.
Oh, well, even better. It's three level.
Okay, so it's three level at the end.
In the heterotic.
There was another question.
So if I have not an I2 fiber, but whatever fiber, do I have 1R per cartan?
Yes, yes, exactly. If you, in general, I can have an arbitrary gauge group. I look at the cartan U1, and then I can refine with respect to every U1 which I want, right? I can take the trace minus 1F, QL, and then Xi1 R1, Xi2 R2, etc.
Oh, okay, so your N, capital N here depends on many more parameters.
Exactly. If I want to refine with respect to several U1s, this is the simplest case where I just have a single one, and I ignore all the others.
Thanks.
Maybe we put a cutoff and we continue with the question after the during the
Okay. Thank you very much.